So my name is Jason McCool. I'm owner of Cool Country Engineering here in Little Rock, Arkansas. And I'm going to walk through some of the code provisions of SPEC 2021 Appendix B and how that impacts our design of CLT shear walls for typical commercial buildings. Then I'll walk through a multi-story high seismic example, try and get into some of the real life issues that we got to work through on stuff like that. And then look at hold down options. The forces can tend to get really big on stuff like this. So what are our options when stuff doesn't work? So let's get started. So for the organization of SPEC, when you first open it up, section 4.6 is very, very short, just a third of a page. It draws in Appendix B, though. That's where the meat of the provisions are. And the other thing it does is it allows an exception for low seismic scenarios of R equals 1.5. So, and I've taken advantage of that before. That gets you out of a lot of the really restrictive requirements of Appendix B. Lets you do more of a performance design. Appendix B, it's also pretty short, only 4 pages, but has a lot of requirements, a lot of limitations built into that 4 pages. The commentary on 4.6 is just 1 paragraph. It's no real information there. It's the commentary on Appendix B, though, is where you get a lot of the background information and a lot of your formulas. If you're trying to develop your own calcs, you've probably already been in that commentary section. Then the R values, it was kind of weird with SPEC 2021 when it came out because it was actually pointing forward to a design standard that hadn't been published yet, ASC 722. But once, now it's not so much an issue since they're both history now, but we got R equals 3 and R equals 4 in the standard table of design coefficients for seismic. You can see they're shown there. They're all limited to 65 foot, all seismic design categories. And just note that these are only bearing wall systems. There's no option for building frame like you'd have with a typical wood sheathed shear wall. So SPEC gives us some give and take here. On the give side, they're giving us platform frame, single or multi-story shear walls with CLT floor diaphragms. So we've got a prescriptive route for a fully timber lateral load path. So that's great. Compared to previous possibilities, we got a little higher R value than what was what we were first looking at possibilities of back in 2016, 2018, that time frame. So we've got R equals 3 for aspect ratios between 2 and 4. R equals 4, but only if all of the walls meet that aspect ratio requirement, which that ends up being a pretty significant requirement. But it is helpful, especially if you're using the R equals 2 like Oregon had initially. So you cut that seismic force in half, so that's nice. But we get a lot of there's a lot of take there. So they take away the option for balloon framing. Now this removes a significant advantage of CLT. Is that size. We can put up huge sections of wood, floors and walls, in one lift with these large panels, but you don't get that if you've got typical floor-to-floor heights with those kind of aspect ratios. Also, uniform panel height, so you're not going to be able to attach your sloping roof directly to the shear wall. You'll have to do a little triangular or a little infill piece as a collector between the diaphragm and the shear wall. Also, no steps in elevation in your shear wall segments. Only CLT floor and roof diaphragms. So if you're looking at maybe doing some kind of hybrid construction, which is getting pretty popular now, then that may interfere with that. No holes, openings, notches, unless you've done rational analysis, which of course we're engineers, so we always want to do rational analysis. But one of the ways we've done that in the past has been with things like tools like force transfer around opening or perforated shear walls. And those are not specifically not allowed for CLT shear walls in Appendix B. So everything's got to be full height segmented shear walls. No screws or custom connections. It's got to be their prescribed shear connectors to account for shear capacity. And then the hold downs have to be designed for amplified loads. Pretty significant amplification there. So we get big tension forces, but we can only count the dead load in the in panel for resisting that overturning moment. And lastly, all of your gravity shear walls have to meet. I mean, all of your gravity CLT walls have to meet the same minimum aspect ratios. No max aspect ratio, but have to meet that minimum as the CLT shear walls. And you have to have all the same shear connections on the top and bottom of the walls, on the vertical joints. You have all the same number of vertical joints, every few feet. The only difference is no hold downs. So that's going to really impact all of your other walls in the building if they're CLT. Here's the big one: the architects may not, be impacted by this as much, but for us engineers, we got to run two analysis models for the lateral load resisting system. So one with shear walls only, which is the one that would naturally come to mind, but another one with the shear walls and any CLT gravity or partition walls, anything not in the lateral force resisting system. And those will factor into your seismic irregularity determination and the structural period. And another thing to keep in mind there is that if your non-LFRS walls are triggering a seismic irregularity, that could also trigger the requirement in ASE 7, section 12.7 for requiring a 3D model, which again, it's kind of starts getting complicated with the way that they want us to handle gravity walls in there. They've got shear resistance, but no direct overturning resistance. It's just kind of makes for some complicated analysis because of that. So the consequences of these limits, of course, it severely limits the mass in mass timber. Instead of having, say, 12-foot wide panels, like the previous project I worked on, we had 11-foot wide shear wall panels, balloon frame. But if I'm doing R equals 4 here, then typical the floor height of 14 foot, I might only have 3.5 feet for my panel widths. So a lot more panels to handle in the field, a lot more connectors to install. And even if I go down to the R equals 3, I'm still not going to max out my panel size. And then this is going to apply to all of my CLT walls on the project. Last project I worked on, we had CLT gravity walls that looked like Swiss cheese because they had tons of doorways, MEP openings, fire sprinkler penetrations, ductwork, you name it. Everything was going through those walls. But it's really going to be hard to do with these requirements on the wall, on even the gravity walls. And then, of course, the two lateral analysis, you got to ask, have I accounted for that increased design time in my project fee? It may not simply double my time. It may be more than that because some of the few software tools that are out there for doing mass timber, may not really be able to handle some of these little nuances that they want. So you may end up having to do a lot more hand calcs on something like this. Now, fortunately, as we're going to see, we can cover a lot of ground with SPEC Toolbox and this module we're demoing today. But for your global analysis model for the building, this can really impact it. The variable floor heights. Architects always want to do, like, say, a grand entrance on the ground floor. Maybe 18-foot lobby and then 14-foot floor-to-floor heights above that. And what that's going to do is we only have 2.5% tolerance on our aspect ratio for the R=4 system. So you can go from an aspect ratio of 3.9 to 4.1 for the commentary. That's it. So now your panels aren't the same width. Your hold downs aren't lining up in the same spots anymore. So there again, more complications to deal with. And then those angle connectors, if you got a topping slab, you may be able to hide a lot of the angle connectors at the base. You may be able to put some trim to hide the ones at the top. But those panel edge connectors are pretty much going to be right at eye level if they're on the exposed side. And you may need so many of them that you can't keep them on an unexposed side, like on the inside of an elevator shaft or something. So behind some drywall on the backside. A lot of clients are wanting exposed timber on the walls and ceilings, so that may really interfere with it. And you got to take that into account early on in the project. And then we like to maximize these panel sizes, especially if you're trying to compete with concrete tilt-up. So balloon framing is great for that, but you're going to be limited to R=1.5 in design categories A and B. Otherwise, you're going to do alternate means and methods approval with your local building authority. MEP routing of ducts, pipes, doors, windows, access hatches, all these things. You're going to need to plan those out a lot more carefully with Appendix B. Prohibit them in your shear walls, or plan on doing a bunch of FEM analysis on it. And there again, strength isn't so much the issue when you've got openings in CLT shear walls. It's more stiffness in your shear wall deflection. It takes a big hit when you got openings. But like I said, this is even affecting your gravity walls, because those requirements are also applying to the gravity walls for the most part. So it's kind of hard to put a doorway in a gravity CLT wall next to your CLT shear wall when you've got panel joints stitched up with metal plates every 3 foot, and you need to put a 3-foot doorway in there. So there's some more things to keep in mind. Now, for loading, a lot of this is basically just like your any other shear wall. You've got your 3 load types: shear, moment, and axial. Your shears coming from wind and seismic, either from the envelope or from the mass of the building itself. Your moments, that's inducing overturning moments in shear walls. And you've got some amount of resisting moment and self-weight and a portion of the building dead load. Where Appendix B differs is it only lets you take the portion of dead load over that end panel. And as we've seen with these aspect ratios, you can end up with some pretty narrow panels. So you may not have much dead load from your floors contributing to the counteracting moment there for your hold downs. And then, of course, the axial loads, you've got your normal gravity loads that any load-bearing wall is going to have. They are on a per-panel basis. And you've got your compression and an amplified tension force for your chord forces on the shear walls. Compression can be resisted by, there's really 6 different bearing interaction models out there. The Eurocode version of this calc, they let you pick which type of model you're looking at, like triangular stress distribution or rectangular or whatever. But SPEDWIZ is just going to kind of lock you into that uniform compression block at that max design stress, and then the hold down on the other side. So it's kind of like a concrete beam analogy with a uniform compression block and a concentrated tension force. The amplified tension force, you can resist it with brackets or continuous tie-down rods. And then due to the platform framing, you're going to have compression perpendicular to the grain at the elevated floor panels. With the foundation, you can take compression parallel to grain if you're not bearing on the face of a CLT panel anymore, or a sill plate or anything. So that helps there. Now jumping into the deflection, equation B-1 is similar to the four-term equation for sheaths, shear walls that you might be familiar with from the commentary for regular wood shear walls. It's just got some adjustments here. So you can see your total shear wall deflection is going to be composed of 5 terms: bending in plane, shear in plane, and then nail slip, which is your sliding term there, horizontal nail slip. And then vertical nail slip gives you your individual panel rotation. And then and you can see that's getting multiplied by your aspect ratio. And then rigid body rotations coming from your hold down stretch and your wood crushing and compression side. So that's basically just like your typical shear walls. And then that's going to determine your deflection of the shear wall, but also the portion of total shear going to each wall on the line, because you've got to maintain that deflection compatibility between walls there. And these stiffnesses are in plane and not the panel properties you would see listed in like PRG 320, Annex A, for instance, or the first table you come to in most CLT supplier catalogs. They're going to give you an EI effective, but it's for bending the panel out of plane, not in plane like this. And you can see the difference just comparing these formulas. The PRG 320 formula here that's your lamination thickness getting cubed there. So you can tell that's bending out of plane. This one, it's the panel width cubed here, so you can tell you're bending in plane there. So they're both labeled EI effective, and sometimes this in plane isn't noted in notation in the formula sometimes, but that's the don't get those confused. So for those of you new to CLT design, that's just little things like that to keep in mind. Now the shear connections, they are very tightly locked down, very prescribed. No leeway here. You use their bracket, their nails. They're not 16-penny common nails. They're box nails. They're bright finish, not galvanized. They're grade 33 brackets, 12 gauge. You don't have any leeway on changing any of that. And so you're using these at the base and top of the walls. You're using these plates at the panel edges. And then not using screws. They do say in the commentary that that's not permitted by Appendix B, but it may be approved by your local building department. The other thing, though, that can come back and bite you if you're not aware of it is they have in the horizontal leg here 2 5/8" bolts or lag screws. And the thing is, these have minimum bearing lengths that actually preclude the 3-ply floor panels that we often like to use for CLT buildings. So just keep that in mind. To use the CLT shear walls, you're going to have to use like the 5-ply panels, and so that's going to affect your gravity design for all the rest of the building, really. And then you can see this is your shear equation for the base connectors, and that really governs everything else on the shear walls, because this is your fuse element for the seismic yielding. So everything ties back to the capacity of these connectors based on mode 3S ductile yielding nails there. Now, so these current provisions, they result in many connections of these small, kind of inefficient panels, at least from a fabrication, and construction standpoint. These panel edge connectors can add up quick. If you've got 5 base connectors down here, and also 5 at the top of the wall. But then if this is an aspect ratio of 4, that means you've got 20 connectors up here. So just looking at a typical example, if I had a 42-foot long shear wall, otherwise I could do like 4 11-foot panels, or I'm sorry, 10.5 foot panels. But now I'm looking at 12 3.5 foot wide panels, and then I've got 5 brackets per panel. That's 8 inches on center. I've got 20 plates going up the vertical joints here. Again, 8 inches on center. 16 nails per connector, 8 nails per connector down here. So, I can easily, like a 4-story building, like I'm going to be showing here in a little bit, I could easily be looking at 5,000 to 10,000 nails per wall, times however many walls you have on your project. So, make sure your contractor going into this knows the field labor that may be involved in this. Now, hold downs, they're not tightly prescribed. You can do typical brackets, nails, screws, bolts. You can do incline screws. That's not prohibited here. Or continuous tie rods. You do have a max hold down deformation of 0.185 inches in the appendix. That is at your design load combination, not the capacity. So for elongation, you're going off the design load combination. For strength, you're going off of an amplified seismic wall capacity, whether 2.0 for seismic or 1.5 for wind. And even with a big, say you're using one of Simpson's bigger brackets, it's still limited, and it's still way short of the capacity you may need for a multi-story high seismic condition with a 2.0 magnification on it. You've still got brittle failure modes to deal with in that boundary element of your CLT, and you just got to get the thing to fit in there. You put all these panels in, all these panel base connectors in here, and the last base connector has to be within 12 inches of the end. So really, your hold downs, you're limited to basically a 12-inch area there. And even if you're putting those near and far side, you can still quickly exceed the capacity of those typical common brackets, like these HDUE ones from Simpson I'm showing here. They're pretty high capacity, but even if I put 3 on each side, 6 of those is not going to do a 200 kip hold down load. So what other options are there? Continuous tie rods is mentioned, and here's just kind of a generic illustration that's in the NDS commentary, SPEC commentary. The nice thing is it does bypass those brittle failure modes, but it's normally only shown for light frame systems. Putting it in between studs in the stud shear wall. So how do you use that with a solid CLT wall? So here's something I've worked out. Again, this is off of the CLT wall, so you don't have those brittle like group tear out and row tear out in that section, the CLT section. Don't have that to deal with. You get a little more room for your base connections there, since you're not taking up any room with hold downs. You can attach those continuous rods to embed plates in the concrete. Your concrete anchorage does have to meet that 2.0 magnified load, so you're definitely going to need to be putting like some hairpins in the concrete foundation. I'm showing these in line with the CLT wall. Testing on these originally back in like 2018, that time frame, was done with these continuous tie rods in front of the wall or on both sides of the wall. That can be an issue. If this is along a corridor or in a egress stair, you don't want these large diameter rods sticking out, stubbing their toes on them, trying to get out the building. So I kind of like doing this in line with the CLT wall. And basically, this is going to get you higher capacities you need, because you can get diameters up to 2 inches. You can get yield strengths up to 130 KSI. It's going to bypass those brittle failure modes. You can use single or multiple rods, like I'm showing 2. I would say 2 max. I would start getting a little uncomfortable adding a whole bunch of rods in line there. If you're wanting to do multiple, I would switch over to like maybe 4 of them, 2 sets of 2, near side and far side, in front of the face of the panels. But again, that may interfere with occupancy issues. You got to design for strength and rod elongation, and that rod elongation a lot of times can govern. So limit states, you're looking at tensile rupture on the net area at the screwed, at the threaded connections. You've got compression parallel to grain as a reaction in the in-panel glue lamp posts. You've got the compression perpendicular to grain, and this is usually what's going to be one of your governing limit states there, because you are getting some big reactions. Like this is a 36 kip, 2 36 kip concentrated loads in a pretty small area here. And then I'm using a glue lamp post to support this, so I've got a really narrow space here, but if I didn't have this post here, bending in that panel could really become an issue. Shear, usually not so much. By the time you account for the compression perpendicular to grain, the shear usually takes care of itself. That, and you're using a 5-ply panel minimum anyway, so so the shears are usually not going to govern. You're also using the net area for elongation of the rods, and really for that, all it's the E of the rods is really what's limiting you. So and then the length. So going up on strength doesn't really help you on that. So usually this will end up being a governing factor on that. And then, like I said, concrete anchorage, you're designing for that amplified load. So like on this case, I ended up having to do a custom size. Like I'm using Simpson ATS rods here and some of their ATUD hold downs, or take-up devices. And that all works with like 1 3/4 rods in this example, but but for that load there, my compression perpendicular to grain wouldn't work unless I use a custom bearing plate there. So things like that to take into account. But that at least gives you an option for these really high loads that you come up with on these higher seismic locations. And so let's get into a live demo of the calculator. And here's a little sample building that I set up. I'm using a bunch of CLT shear walls in the core, and then I've done 6 outer shear walls behind this glass facade. And this is a 4-story office building in Paragould, Arkansas, right next to the or close to the New Madrid fault line. So pretty high seismic, and you can see just here's what I'm using for my my building design. Just trying to get some realistic loads for this. And here you can see my wind base shear is 268 kips max. My seismic base shear is 754 kips, so I'm only going to be looking at seismic on this. But I'm using the RX 4 high aspect ratio walls for this. And so now let's swap over to my calculator here. Okay, so this is the shear wall calculator for the US in SPEC Toolbox. So you can see here I can pick my CLT supplier, and then what I've done is filtered for this Conway plant. I'm using a Mercer. It has a plant like an hour away from my house and probably just maybe 3 hours away from the job site in this example. So this lets you can see you can pick different suppliers. You could pick a PRG 320 if you wanted to do a manufacturer independent baseline for a preliminary bid or something. But I'm going through and picking my Southern Pine that I love using here, and picking one of their E grades. And then I've picked my 7-ply wall layup. And since compression perpendicular to grain affects your compression sizing of the compression end zone for your CLT wall, you do need to account for your floor layup. So I'm using a 5-ply panel for the floor, and then you put in your shear and compression perpendicular to grain. And then I'm using 5.5-inch typical lamellas, 3'8" panel widths. I'm assuming a 1-foot tension strip. Like I said, that's kind of my max that I can do without starting to interfere with those base angle connectors. And since I did a 22-foot wide shear wall, then I'm using 6 panels, and I think I actually, let me go back here. I think I've got, yes, okay. Let me give you a little bit more background here. I'm going to have like 200 kip hold down forces on here, and then seismic easily governed. I did do a rigid diaphragm analysis and came up with this wall being the one of interest here. And then I distributed my loads with equivalent lateral force. So I've got 56.5 kips of storey shear there at my second level there. And then that breaks down into these uniform loads at each level. So you'll see that already put into my my calculator entry there. So and then I'm using 0.025 for my drift ratio per SE7. So now let's jump back to that calculator, and you'll see some of those numbers showing up in here. So we've got these panels. Having to use a tie rod system, which isn't accounted for in SPEC Toolbox yet, but you know, one thing I love about SPEC Toolbox is they're always adding new things. So hopefully that'll be in there soon. But right now, you know, if you have brackets, you can look up your published values from like a Simpson catalog, or you know, another hold down manufacturer, and you can put in some of this information here, and it'll start taking that into account for your net section, group tear out and row tear out, your brittle failure modes. You're putting in your number of rows of screws and spacing of screws in the row and between rows. And then for my loading, seismic, 4 stories. So putting in floor to floor height, my forces at each level that I showed you earlier from that the equivalent lateral force distribution. And then it's going to tally these up for that that storey shear. Then I came up with these gravity loads at my floor levels and roof. I'm putting in 8 brackets at the base of each wall on the first floor, and then I can pull back a little bit on that next floor, and then go down to 5, and then finally down to 2. And you can see over here, I can make changes in here and see how it affects from a 3D view there, or and also how it affects. So like say, I'll leave this open here, and you can see my angle brackets are at 92%. So one thing I love here is just this kind of instant feedback in here. So let's say I want to just see, can I go down to 7 on the first level? And nope, just over. So that tells me what I need to know there. And can I go down on a higher level? Nope, I am As you can see, I've already put this stuff in, so I'm already kind of maxed out at every level. Now, and then we can always dig into the details afterwards and see exactly where the different max stress ratios are. But you got this kind of nice little go, no-go gauge here showing you, green and red lights for each condition. So like I can see, shear, usually that's not an issue. Usually it's always the connectors governing on CLT shear walls, because the CLT panels themselves are very rigid. So shear is expectedly low. Compression, similar. It's usually not an issue. It's usually always going to be my connections that are governing. And then back here. Okay. So then we've got that put in. You can put in your number of hold downs, and in this case, really that top level is the only one that I'm really going to be able to do traditional hold downs on. Maybe the top 2 floors, these bottom 2 floors, I'm going to have to do tie rods. But that's one thing I wanted to kind of work through in this presentation is, what do you do? Like a lot of the examples I've seen worked out in the past, just looked at lower seismic where you could make typical stuff work out. So that's why I wanted to show a really high seismic case like this and just work through, is there options? Yes, there is options. They're not really very common right now, but they are out there. So so in this case, here's my this is my inelastic deformation, and then got my C sub D factor, reducing that, so it'd be like 1.5 inches elastic deflection. Here's my hold down deflection. That's coming from a publisher's catalog for at LRFD values. And then you can see I'm using LRFD here. You can do ASD or LRFD in SPEC Toolbox. I'm using LRFD just because everything's kind of geared towards LRFD for seismic anyway. And then you're going to be doing that for your concrete anchorage, and even with this, even your deflection for your hold downs is at LRFD load combos, so it just kind of makes sense to do that. Then you've got output summary here that's going to break down all the different portions of your calcs, and this hold down failure and the barrel failure, hold down deformation, none of that's really surprising because I've got 200 kips. That's too much for any hold down on the market. I've done some custom hold downs for using that shear walls in that exception, the R equals 1.5 exception. I've done some custom hold downs that were good for 366 kips by LRFD, but they were too big to fit in that 12-inch width. So really nothing is going to work within the constraints of Appendix B when you start getting up to these kind of loads, other than a continuous tie rod. So this doesn't really surprise me seeing these failures, and there's really not much we can do about them with traditional hold down brackets. But the one thing here is that SPEC Toolbox is covering a lot of ground calc-wise. So I can do some manual calcs on those continuous tie rods, or if I'm delegating that to somebody like Simpson, then they're going to do a lot of those calcs for me. So, but SPEC Toolbox is doing like kind of the lion's share of the work here for me, because they're doing all of my my property calculations. So here's my E, my modulus elasticity, my axial and shear. Here's all my properties. I can go through and check these to make sure, is this matching up with like product catalogs? Is it what I think it is? I've got my formulas shown. One thing I always hate is trying to verify calcs where it's just a sheet of numbers, just output and no background. So I love seeing formulas. I love seeing reference citations to where stuff came from. And you'll see that in a lot of the SPEC